So we're now ready to make our robot navigate autonomously so that we don't need to remotely control the robot through the teleop. Our solution is going to assume a known starting location and known map of the environment. Nevertheless, it's pretty exciting to make our first step into the world of making robots move on their own. This process is going to have three key steps. First, we're going to incorporate the ROS Navigation Stack into our model by creating the appropriate launch files. We're then going to teleop our robot to create a map of our environment. And finally, the robot will use this map to then autonomously navigate through our world. Now, this video is going to be split into two pieces. These steps are pretty well documented in other tutorials, so please refer to them for additional details. In particular, we have the navigation stack, the creating the map, and also the autonomous navigation. First, I'm going to see how the Tutorial bot behaves when using the ROS Navigation Stack, and then we're going to apply this to our own robot afterwards. When using the ROS Navigation Stack, there's three main steps. There's first creating the map, saving the map, and then using the map. And with the Tutorial tutorial, it's pretty straightforward. So we'll just launch these in separate terminals. So basically we're going to teleop the robot around, make sure it views different parts of the environment, and over time we're going to accumulate a map over time. And you can sort of see the map getting filled in here. As we start to rotate and see more objects, it sort of aligns them nicely. And there we go, filling in more. And so in this example, you'll notice that our map is really quite confused. It thinks the pillar is here and also there, and that this box is somehow over here as well as here. So G-mapping in this case doesn't work perfectly because it relies on particle filters, which is basically just a set of reasonable guesses about what the map looks like. Each possible map is called a particle, and these particles are continuously updated as new sensor data from the laser arrives. Unfortunately, these particles can't really recover once they've been led astray. So you'll see as I continue to move the robot around, we're sort of adding pieces to the map, sort of nonsensically. Now, G-mapping is incorporating each laser scan update by matching it to each of the particles' guesses about what the maps look like via a process called scan matching. Now, scan matching tends to work well when the features are unique and dense. Which also means that naturally G-mapping will suffer in sparse situations where maybe if you're only looking at maybe one side of an object that's really not unique at all and looks just like the side of every other object. And this, of course, will then lead to these sort of erroneous maps. And so let's go ahead and try and recreate this map again and give you a sense of what a good map looks like. Okay, so basically you'll know that your map's correct when the gaps in the spaces, like these ones, are blocked because of the obstacles. If it's not the case, then you'll probably have to redo this process, or else the robot's unlikely to navigate properly. And so you'll notice once you create the map that you get two files. You get a YAML file and you get a PGM file. The YAML file will actually point to this PGM file. So if you move this file around, you're going to have to redirect that path to point to this guy. So at this point, you basically created a map of the environment. we're going to be using AMCL for navigation. AMCL also uses particle filters, but instead of particles to estimate a map of the environment, these particles are estimating the state of the robot, namely its position and orientation, which is referred to as the robot's pose. And now to make the robot go to a position, we press 2D nav goal and point to anywhere, left click, and then drag to a particular direction. And you'll see that the robot turns and actually goes to navigate there all on its own. Notice that if I give the robot a goal that's pretty far away that goes through an obstacle, that it actually safely goes around it and doesn't collide into anything. So now for our robot, let's start with the previous Git repo package. So I'm going to take my branch, I'm going to download the zip file with the navigation code, and we'll just move things over as needed. Now first, I've made some changes to the actual robot model. Next, we'll need to create a new navigation package. Now from the code that I pushed, we're going to copy over the launch file. And also the teleop one. Notice that I'm running the Turtlebot teleop package, except I'm just remapping from this command velocity message to this one, which is what our robot subscribes to. For the gmapping launch file, we're just launching the gmapping node and setting some parameters. A really good place for examples is actually just to go to the Turtlebot packages. And if you view these launch files for the Turtlebot, they're basically doing the exact same thing, except they might be filling in a couple more parameters here. In any case, these Turtlebot launch files are a great place for additional examples. One difference I'm going to make is import the Turtlebot's world, just so we're in the same environment. And then I'm just going to copy over this world file launcher, and all it does is load the Turtlebot world instead of my original world. So now let's launch this gazebo world. In the repo, I've created a custom RViz file. But just to show you, let me show you how you can make your own custom RViz file. So once again, we're going to add the robot model and a map now. Since we actually have gmapping running, we're going to switch the topic to the map. And basically this will show what is accumulated so far as the map. So once we launch our custom teleop, and now we'll be able to assemble a map just like we did for the Turtlebot. This is a pretty good map now. I noticed it was actually a bit easier for us this time, since the simulated sensor here has a much wider field of view than it did for the Turtlebot. It makes it a lot easier for the scan matching to happen, which of course then means that the particles for the maps tend to be more accurate. So now we're going to save it. Now I can also save the RViz file. So now if I wanted to load my custom RViz file, I'll just go into Launch File. and make it launch the specific ROS file that I created. So you notice now it's loaded with our original parameters with the laser and the robot and the map itself. So saving these ROS files is really nice. So now the final step is to then load the map, and we'll need a couple new launch files to help that out. Our gazebo file is fine. Our navigation launch file is new. And so we're going to have a new one called AMCL demo. And this launch file is going to basically launch localization as AMCL, and we're specifying a differential drive robot. We also need to specify a couple parameters files. See, all these config files can be tweaked, and so I would recommend reading up on them to better understand what exactly you're tweaking. So I'm just going to bring over a custom ROS file to help out with the visualizations. So it looks like we've actually successfully mapped out our obstacles. So now let's set navigation goals for our robot to follow. And you'll see that our robot, just like it did for the turtle bot, is able to compute a path that doesn't run into obstacles. Now you'll notice that the robot does in fact move a little bit more funny and less smooth than the turtle bot. That's clearly because there's something wrong with our URDF file. And so if anyone has any suggestions on how to improve this, definitely would be appreciated. I've added visualizations for the paths. So the local path is identified as in green, this little thin green line here, and the global path, where it's going, is represented in blue here. So I give it a destination of right here, and so the robot's slowly making its way around to that point. And you'll notice that because the robot doesn't perfectly track the path being given to it, it sort of ran into the obstacle, and since it's too close, it needs to find another behavior to get around it. And that's why it kind of got stuck there for a little bit. So at this point, we've successfully created an autonomous simulation robot from the ground up, thanks to ROS and Gazebo. I hope you better understand now what's running behind the scenes to make this basic robot work. You now have the opportunity to extend this in numerous different directions, so good luck.